Basically, I'm here today to talk to you about I/O monitoring and scheduling in high-performance computing environments. This is an open systems initiative that we're trying to put together with Cray and one of our partners / customers, Oak Ridge National Labs. And I'm here today to present this information to you to see how much interest there might be in a more general context, the general computing community. So basically, what is this? What isn't it? Who is Cray today? We're going to talk a little bit about one of our customers. So the first two slides are kind of like the marketing. Then we're going to get into a little architecture detail about what HPC processing and storage, what do we do, I/O monitoring and scheduling. Then we're going to get into specific problems we have in technical computing and how they might relate to the more general cloud computing, enterprise computing space. These things like pre and post staging of data, dynamic and static quality of service, and I will use the quality of service moniker, unlike our last speaker. I'm not a telecommunications guy, so I don't bring that baggage with me. We're going to talk a little bit about the approach to resolving these. We're going to talk about the distributed architecture around IOMS, a little bit about standards, how we develop modules, and why standards are not entirely adequate, and what we're going to look at doing for trying to provide a prototype, some of the technical challenges, whether the value is for what I perceive possibly the more general computing environments, and longer-term possibilities and next steps. So we have roughly 20 slides to get through here, so we'll get this going here real quickly. So this isn't a product you can buy, evaluate, or look at today. We're talking about an open systems initiative. This is based off a conversation we've been having over the last 4 to 5 weeks with some of our customers within Cray and with some Cray people internally. So this is strictly an open systems initiative. This is not something you're going to pull off the shelf today. So a little bit about Cray. Basically, Cray, for anyone who's got gray hair or is losing their hair, or is a combination of both, like I am. Cray is formed from, it was basically reformulated in April of 2000 as Cray Inc. We're a spin-off of SGI. We were originally called Cray Research. In the year 2000, we were joined together with a company called Terra up in Seattle. We maintain, as you can see here, 4 development offices, engineering in Austin, Minneapolis, and Chippewa, and then our corporate headquarters is up in Seattle. And today we employ about, I think, 900 people would be closer to the correct number. So we deal strictly with mostly high-end computing. We do some small departmental supercomputing, but most of our focus is on the high end. One of our customers is Oak Ridge National Labs. This is a 1.6 petaflop system called Jaguar at Oak Ridge. It is basically, you can see some of the statistics here, 10 petabytes of central storage, 26,000 nodes computationally, roughly 181,000 AMD cores, which is 45,000 quad-core Opterons, a whole bunch of memory, and about 284 gigabytes per second of disk bandwidth coming out of the system. The important things for this talk is to focus on the central storage aspects and the gigabyte per second aspect of storage and I/O. Also, previously, if you visit that URL, you'll find some real interesting things that Oak Ridge is doing with that, in case you're interested in the science of scale, computational engineering, that sort of thing. There's some very interesting slides and videos at the Oak Ridge site, so please visit it. So HPC processing and storage, what is it? For some of those who may not be aware of what we're talking about here. Today, processing-wise, most traditional HPC systems still use what we call batch complexes or batch systems to load and monitor jobs. A batch system provides an ability to basically state precursor to the job run, how many nodes you need, how much memory you need, what type of files you're going to utilize, how long you think the job is going to run, and that's the way scheduling is done on these tens of thousands of node systems. If you spend $20 million on one of these, you don't want it sitting idle, okay? So you've got a multi-million-dollar investment. You want to schedule as much scientific and engineering work through the system as you possibly can get, so you want to push it through relatively quickly. So the facilities we're dealing with are focusing on really sustaining maximum bandwidth, performance, and to minimize turnaround time for science at scale. Petascale problems can utilize a large percentage of the systems for extended runtimes. So science at scale problems can use a system like Jaguar for up to several weeks at a time, depending on the type of problems they're working on. So you're talking energy research, possibly human genome, protein folding sorts of problems, climate studies for climate change, combustion research, so very large-scale engineering sorts of problems. So storage-wise, within a lot of Cray's customers today have two distinct models of storage. We have dedicated, and then there's shared. We also have some customers who do like a mixed mode model, I'll call it, where they're doing also, a dedicated for one system and shared for another. You'll see a little bit more clarification on the next slide. Again, focusing to maximize sustained performance and minimize turnaround time. And the data sets are growing without bound. So it's very much like general technical computing. And in the future, we're talking exascale computing. So not just exascale storage and I/O, but exascale performance, 10 to the 18th. So what are we talking about here with monitoring and scheduling? What are we talking about? Basically, what we want to do is this is a tentative effort to establish a server and protocol and an architecture to interconnect batch-based systems to mechanisms that assist us in monitoring and scheduling I/O. So today, as I mentioned, we have batch complexes that allow us to for the users to specify how many nodes they're going to use, how many cores they're going to use, how much runtime they're going to be utilizing off the system. We don't have anything that does the equivalent for I/O. So the bandwidth is very much like some people have stated in the past, a cloud computing problem where you allocate a certain number of nodes, a certain hierarchy for people to use a complex or a cluster within a cloud computing environment, but you really have no way of controlling the I/O. But we do it on a batch basis where in cloud computing or traditional IT, you're doing an interactive basis. So we're trying to balance these things, and really the problem sets we're trying to address is pre- and post-staging of data for local and remote facilities, static quality of service, and dynamic quality of service. So to give you an idea of what we mean when we say pre- and post-staging of data, imagine trying to move data around a center, a large center that might have two large computational systems and a visualization system. These would be individual clusters. This might be like Jaguar. Oak Ridge has a large visualization system, what they call a power wall, which is a 24-node cluster that runs a large visualization display so scientists can come in and look at their data. And they might have a third or fourth computational system off doing something else. So on the left-hand side, you see an example of what we would call dedicated storage. On the right-hand side, you'd see an example of what we call shared storage. Strictly speaking, each system on the left has its own storage pool, where the system on the right, or all the systems on the right, address a single storage pool. This is the case at Oak Ridge National Labs. This storage pool is 10 petabytes of high-performance storage that's shared using a Lustre file system amongst multiple systems within the center. The problem here for our users in this situation is you can have processes, jobs running on multiple systems. Let's say you have a higher priority job running on computational system A, and someone's trying to do visualization off the visualization server. Or you might have someone at a higher priority on computational system B. That's affected all to the single quality of service point, which is your primary storage pool. Your bandwidth, despite the fact that you spent $20, $30, $40 million in developing a facility, is still somewhat limited because it can be extremely expensive. So what we want to do is come up with a mechanism that allows us to address basically the ability to schedule this I/O movement within to and out of the center. So when we say static quality of service, what we mean is we might have BP, which means batch process, running here on each one of these computational systems. In this case, on the right-hand side, addressing all three storage or data points, on this primary storage pool. And on the left, you have the exact same thing, only you have your own dedicated storage pool. As you can see on the right, this could potentially be a problem if someone starts to use more bandwidth into this available storage pool. Let's say someone on computational system B is using a lot of the bandwidth when computational system A is trying to run a science at scale sort of problem. And so that person gets bandwidth starved, or that job gets bandwidth starved. So it's a bit of an issue for us. Then we also run into something we call dynamic quality of service, which is checkpointing. So if you have a job that runs for many weeks on a large-scale system, and you have to take the system down for servicing, maintenance, it fails for some reason because you've got 20,000 nodes, and there's a possibility of failure. people often do what we call checkpoint. Checkpoint is simply, they'll dump the contents of a large percentage of the machine's memory into a checkpoint file that will allow them to restart the job at that point in time. So if you run for 5 days, you checkpoint once every hour. If the system fails after 5 days, you're back, and when the system restarts, you're back at 5 days minus 1 hour. So you don't throw away the time you've run. So this might happen every hour, and this is what we call a checkpoint shift here. So this becomes more of a dynamic issue for us. How do we adjust the bandwidth within the quality of service to our central storage pool to allow this checkpoint to occur once an hour, but to not starve these other jobs in the center? And today, again, there is no mechanism to do this. So how do we resolve these difficulties? What we're looking at today for this project is to basically create an abstraction layer between what we view as the computational systems. Here on the left, you see a whole bunch of batch systems names, different types of batch systems there. There's PBS Pro, Load Sharing Facility, Torque, Moab, SunGrid Engine, some of these names you might recognize. Some of these are commercial products, other ones are open source products that you can download off the web today. Slurm, Load Leveler. And here's a list of all of the different things we commonly find in some of these facilities for Cray customers and for other customers as well in the high-performance computing environment. Whether those are HSMs, hierarchical storage managers, distributed file system or cluster file systems, things like Lustre or NFS v3, v4, global parallel file system from IBM, QFS or shared QFS. So you have all these possible different file systems, HSM products, and bulk high-speed data transfer elements that interact with the internet to pull information from grids or scientific instruments. So you have typical things that you probably are aware of: grid FTP, SCP, Axle. So you have all these different mechanisms in play. And what we're trying to do is put some intelligence in between the computational systems and the physical storage. Today, with the advent of object storage technology, OSD, with a lot more capability, multi-core capability, VNIC capability here, we actually can start steering the storage pools to adjust the quality of service and do some scheduling proactively. And the other thing I'd like to point out is HSMs. If you're aware of a traditional HSM, you might say, get a file. The file's not there. It opens up an inode. It goes out, talks to a tape robot to pull in some data. Could you imagine that problem if you have to move 2 petabytes off an HSM? So you say, I'm going to take 10,000 nodes, but I need to get my 2 petabytes of data. You lock up 10,000 nodes while you wait for 2 petabytes of data to move in off the HSM. Not a very efficient utilization of your system. So what are we talking about here? Again, a basic client-server architecture where we would put a system either writing on top of directly or in front of our storage pool, and we would have a client back on our computational system. And you would have a discrete protocol running between the two, which would be out of band from your primary file system access. And I don't care in this particular instance if that's NFS, Lustre, whatever it is, Hadoop, don't care. So basically, we need to develop standards to enable us to do this. That standard would include a protocol, what we just call the IMS protocol, which today we view as possibly running on top of SCTP, because it was originally developed for Signaling System 7, has IP multi-homing and multi-streaming capability. And on the back end, we would view this much like Apache runs today, where you could have an open API with plugins or modules that would allow you to talk to vendor-specific storage technology in the back. So for someone like Sun, with their Amber Road product, let's just pick something here, a 7000 series, they could say, we're going to make this capable of interacting with the system, and they could have an Amber Road plugin that they provide you that plugs into the server so you can guide things through the IMS protocol. And this would allow you to adjust quality of service. So there'd be a bunch of required replicated modules here, and there would be a vendor-specific module. And the vendors might be even go as far as providing their own servers. We really don't care as long as they're compliant to a standard that would be developed. The standard for the front-end protocol, the standard for the module. Okay, so a little bit about modules and how this might possibly work. You have a specified API. There's a certain number of modules which would be required. Those would dictate things like security, the dictionary, the versioning and control information for the protocol, the management API, and the scheduling. Those would be required modules, fundamental. Monitoring and control would be implementation specific to the back-end storage that you have. So that might be file system specific. It might implement dtrace, virtual machines, or virtual machine NICs using Crossbow technology, or have firewire or firmware-based control, primarily firewire. And your request and information and response and acknowledgement would flow through the system into these modules and be handled discreetly. So our standards are not entirely adequate. We could develop standards until we're blue in the face. That won't be probably acceptable to the industry as a whole. I firmly believe that what needs to be done is to develop a prototype, much like the web wasn't really widely accepted until a web server was available for download openly to people to use and experiment with. Both a web server and a browser was what made the World Wide Web really possible. So what would a prototype potentially look like? Here's a rough diagram, very high-level view. So again, modules on the back, standard module control, pipeline, both receive and transmit queue, an IMS client that sits on a head node for your computational cluster, and you would have this discrete activity going back and in. And we have a front end and a back end just for specification of the architecture. So what are our technical challenges here? So our abstraction to quantify I/O requirements, our API requirements, we need to provide a flexible protocol. The back-end, server-to-server back-end protocol needs to be scalable and support multiple servers. We need to have a majority of the server functionality needs to be provided by modules, which I've already discussed. And there's a bunch of other things here. Quality of services challenges for remote versus local resources. That's where you're talking about grid data movement. Order execution and precedence between modules needs to be viable. So if you look at Apache, the way Apache implements modules really wouldn't work for this. The concept would work, but the precedence and ordering typical of Apache doesn't really work for this sort of system. All right, so I've been up here rambling on and on and on. So why should you care what we do in Oak Ridge or Lawrence Livermore or wherever, high performance computing users, why should you care? You're running a cloud facility, you're running your general technical computing facility. So, okay, for your users, this would potentially allow users to build or buy best-in-class systems based on standardized elements. I don't care if you're buying Amber Road, I don't care if you're buying NetApp, I don't care if you're buying BlueArc, I don't care if you're buying Lustre, but if you have a way to control your bandwidth and your latency, your metadata performance, and it's a standardized mechanism, and all the vendors support it, that's a winning case for users, for consumers of the technology. We want to increase the utilization of the system. We want to provide a mechanism to regulate and prioritize data flow. And for vendors, why would the vendors do this? Well, if I'm a storage vendor and I come to you today and I say, well, I've got a gigabyte of storage, and you say, well, I've got someone else lined up in front of you, how much are you going to sell it to me for? And I say, well, it's $1.25 today. And you go, well, the guy next door is selling it to me for $1.10. Thanks for playing. So what's happening with vendors on the storage market is really it's becoming an issue of cost density per gigabyte. They have no way of doing any innovation. So this might provide one more way for them to be innovative. Maybe they provide you with a scheduler module that's much more effective than the next guy over. Maybe Sun can provide an implementation that rides on Crossbow that's much more effective as far as bandwidth consumption is concerned. So this provides them with another way to compete for your business. Okay. So generally, why should you care? If you're running a cloud computing facility, you have 3 tiers of users in our example, tier 1, tier 2, tier 3, and maybe they're charged at different rates. And they're coming into your cluster, and they're running you're running web or edge services on your cluster, and maybe the tier 1 guy is paying a premium price. Well, if tier 1 user comes in and you have this client, a lightweight client with hooks, or maybe you're running Solaris, so you could run this on top of dtrace. You know when he opens a file. You know that he's a tier 1 user. You can map it back into the IMS server using the protocol, and the IMS server can adjust your bandwidth and quality of service for that particular node or VM. So that enables you to prioritize your tiers of users. Or maybe you do it on a service level, or maybe you do it on the type of application they're running. Maybe you don't like Britney Spears videos. So you turn down, the quality of service for all Britney Spears videos. I don't know. But it gives you a capability and control within your facility potentially that you don't have today. So basically where we're at is We're going to do some initial protocol design works and specifications for what I call a V01 release, S2S protocol design spec for V01, and some draft codification experimental plugin framework work on what the server would look like. I was going to present this at a BOF at FAST, but unfortunately I have to leave town tomorrow morning, so I won't be around for FAST. But you know, if you have, so basically in conclusion, if you have an interest in this, please let me know. I can be reached at the email at the top of the slide deck. And I'm also have some business cards here I can hand out to folks. So if you have any interest, please let us know. Again, this is not something that Cray's involved in per se because we're trying to sell you something, because we're really not in this market space. But we view this as if it's an open systems initiative and we got a lot more consumers of the technology involved, it provides us with a lot more leverage because Cray does not buy, despite 10 petabyte installations, we don't buy as much as everyone in the general IT community.